Okay, damped harmonic motion. So simple harmonic motion has a constant amplitude and it goes on forever. So if you think about it, if you're modelling something with a sine wave, it's just going to oscillate forever, which is great in theory. In practice, amplitude will decrease over time and motion will die away due to resistive forces. So we can use second order differential equations to model this, and this is known as damped harmonic motion. So these will slow down. The motion will slow down over time and the amplitude will decrease at a varying rate depending on the type of damped harmonic motion, which I'll talk through in the next few examples. So, oh sorry, that wasn't meant to be that. This is the equation for damped harmonic motion. That's omega squared again. This doesn't relate to the period this time, so just keep an eye on that. And K is a positive constant. Omega squared is obviously positive, and K is also positive. So as an example, we've got a damped oscillating system modelled by this differential equation when t is 0, x is 0, and v is 1. And we can solve this for like 3 different values of k. We're just going to be relating into the discriminant and looking at how that affects the motion. So we'll start with k equals 26. I'll leave you to copy that down for your notes. And when k is 26, we get this equation here. Solving these isn't too bad. You've done a lot of this, as you know. So the auxiliary equation is m squared plus 26m plus 25 equals 0. This gives you m is equal to minus 1, or m is equal to minus 25. So we've got 2 real roots for this one, and x is equal to e to the minus t. Sorry, I forgot my constant. X is equal to ae to the minus t plus be to the minus 25t. And then we can use those initial boundary conditions to find a and b. So t equals 0, x equals 0. That gives you a plus b equals 0. And we also know the velocity is 1 when t is 0. So I can differentiate x to get to the velocity. And that is equal to minus a e to the minus t minus 25b e to the minus 25t. And so substituting into there, v is 1 when t is 0, which takes us to there. And then we've got 2 simultaneous equations. So these should be feeling quite routine, hopefully. And a is 1 over 24. And b comes out as being minus 1 over 24. So you can use your calculator for that. And so x is equal to 1 over 24 e to the minus t minus 1 over 24 e to the minus 25t. If you were going to draw a graph that, you don't need to be able to draw these, so don't worry. So you could put that into a graphing package. You could differentiate this to find where the maximum point is. I'll do that in an example later on, I think. So if you differentiate that, you will find the maximum is where t is positive. And this one here, when t is 0, x is 0. So we're doing x against t. And there will be a maximum here. As t approaches infinity, these are both going to 0, and this one will come down like this. So there won't be any oscillations for this function. It may start positive, so you might start with a positive displacement. If a or b are 0, then you will literally just have a exponential decay sort of situation, and it will just look like that. So there's various ways that graph can look, but the important thing really to note is there's actually no oscillations for that. This is because the resistive force is large compared to the restoring force. So the restoring force on the spring, for instance, won't be enough to overcome the resistive force, essentially. So two things, or a few things to note with this. So for this one here, the discriminant, I'll let you work it out if you want to. Can I spell discriminant of the auxiliary equation is greater than 0. Well, we know it is because we've got two roots. And the roots are negative. They will always be negative for these because of the form of the differential equation. These are both positive, which will make those roots negative. So that's kind of your conditions. Discriminant bigger than 0, two negative roots. And in this case, and this will always be true, not just for this example, the system decays without oscillating. And I think it'd be wise to kind of realise that this is what happens for a positive discriminant. And this is called heavy damping. It's also called over-damping. I think heavy damping is kind of an easier one to remember. But in case you see that anywhere, you can also call that over-damping. So it doesn't feel wildly exciting because we've no longer got these nice oscillations. So the next example, we can look at ones which, continue to oscillate, but the amplitude gets smaller over time. So that's the first example. I better stop the video because I don't think my phone can handle anymore.